Hey everyone, we are here today to talk a little bit about electricity. So, as you recall, yesterday we talked about electricity as the flow of electrons through a material. And we learned that there are some materials, which we call conductors, that allow that flow to happen very easily. And then there are some materials that we call insulators that don't really allow for that flow. And obviously with most things in physics, like we set this like black white line, and the reality is a little grayer, right? Some materials do allow some flow of electricity, but not a lot. There are bad conductors, there are bad insulators. But generally speaking, when we're talking about this, we talk about it as though they're all working perfectly. We also talked a little bit about the big ideas of voltage, current, and resistance. Voltage being essentially how much energy the electrons have, current being how many of them are moving past a specific place at a specific time, and then resistance being how easy it is for those to move. And so today we're going to talk about relating those because I think a lot of you, when we started talking about that, thought, well, those aren't necessarily independent ideas, right? That after all, a voltage, how much energy you have, is going to determine how quickly the electrons are moving, and that's going to determine how many of them go past a certain place at a certain time. Or if it's really hard for the electrons to move, that's going to affect um, how many electrons can get past a certain place at a certain time. And you're completely correct about that. And so those relationships were first studied by a man by the name of Ohm. And so we are going to talk about Ohm today, and specifically, we're going to talk about Ohm's law. All right, so Ohm's law tells us the relationship between voltage, current, and resistance. And the way we usually write it is that V equals IR. So the voltage is equal to the current times resistance. Now, I'll be honest, I actually like to rearrange this a little bit and look at it a slightly different way if I'm trying to understand it. How much current we have is related to both how much voltage we have and how much resistance we have. So if this voltage goes up, the current's going to go up. Those are directly proportional to each other. There's a linear relationship between them. But if this resistance goes up, then the current goes down. There's an inverse relationship between those two. And that should make sense if we think back to our analogies, right? That if they have more energy, I'm expecting to have more of them pass a certain place at a certain time. But if it's harder for them to travel, I'm expecting them to have fewer electrons moving at any given time. So let's go ahead and try a couple of practice problems here. Um, and one of the things I really like about Ohm's law, and we're going to study this as we get into circuit arrangements and as we start talking about Kirchhoff's laws next week. One of the things I really like about Ohm's law is that it works on every possible scale. So what we're going to talk about today is like the circuit level scale. So we're going to talk about the battery for a circuit, the circuit's total resistance, and what the current flowing through that circuit is going to be, kind of the biggest level possible. But next class, we'll talk a little bit about the device scale. And the cool thing about Ohm's law is that it works at both of these scales. And so we will end up using Ohm's law over and over and over again as we're studying circuits. So here, let's say that I have an 18-volt battery hooked up to a circuit with a resistance of 6 ohms. Remember, this is the Greek letter omega, and it stands for the unit ohms, and yes, it's the same ohm as Ohm's law. All right, so let's think about Ohm's law, V equals IR. And we're going to ask how much current is in this circuit. So we'll figure out what we've got. We've got an 18-volt battery. That's going to be our voltage. And we've got a resistance of 6 ohms. That's going to be our resistance. And then we'll solve for current. So 18 equals I times 6. Divide both sides by 6. And we'll get a current of 3 amps. Let's try one more. So I have a 5 amp current flowing through a circuit with a resistance of 2 ohms. What is the voltage? So we're going to bust out V equals IR again. Let's think about what we have. We have a current, which is going to be I. And we have a resistance, which is going to be R. So the voltage is equal to the current times the resistance, and that is 10 volts. One thing that you will notice as we start to do problems in electricity is that all of these units are actually really, really big. What I mean by that is that when we came along and defined what a volt is and what an amp is and what a little less so what a ohm is, but later on in AP we cover things like farads and Teslas. The way that they were initially defined makes them really, really, really huge. So like 1 amp is actually a lot of current. And so do notice, like as you start to see some practice problems with these, you are going to maybe notice sometimes that we're dealing a lot with smaller numbers. And that's because of just how they were defined. While a meter is very human-sized and a second is very human-sized, an amp and a volt are not actually very human-sized. And so don't be surprised if you see things that are in milliamps. That is a much more common realistic measure of what kinds of currents we're dealing with. All right. Thanks so much. Bye.